Let's take a look at 6.3 on arc length. We will go through the entire derivation of it and a few things to remember. So here we go. So first, let's let P be the point x1, y1, and Q, x2, y2, be points in the xy plane. And let's recall how to find the distance between them, because it's going to, our arc length formula is going to be based off of little line segments, and the distance between 2 points is a line segment. Okay, so our goal is to find the distance between them, between P and Q. So this is how you derive it. So you may have seen this all before, but I'm going to be a little more rigorous than you would have seen like in algebra. So you have a point P, and that's x1, y1. And then another point up here, say Q, and that'll be x2, y2. And we want to find the distance between them. So we want to find this distance, and we'll call that distance D. And so you probably would know that you use a right triangle and the Pythagorean theorem. So this length here is the x values, and you can say this in general, that is the absolute value of x2 minus x1. It doesn't matter the order, right? Because I'm taking the absolute value and I gave you P, but I could have just put Q over here. So Q can be anywhere. So if I do it like that, it's always that distance. And similarly, the y is y2 minus y1. So then the distance formula, D, is we use Pythagorean theorem, x squared plus y squared is the hypotenuse squared. So what you get then is that D is equal to plus or minus the square root, but we use, of course, just the positive square root. And when you take the square of the difference like that, you don't need absolute values. So I'm going to speed things up a bit, and you get x2 minus x1 squared plus y2 minus 1 squared. Okay, so you've seen that all before. All right, so that's the distance formula. What we want to do is this, our goal. We want to find the length of a smooth curve. I'm going to define a smooth curve in R2. So R2 is the xy plane. When we say R2, what we mean is the xy plane. So we have a smooth curve, and I'll define what smooth means. We have a smooth curve like that, suppose. And what we end up doing is looking at these line segments. So we end up saying this is, say, Q naught, and then we break it up into pieces. This will be, say, Q1, and then Q2, kind of exaggerating a little bit here, so Q3, etc. So then you can approximate the curve length by looking at these line segments. Okay, and so you can see there, Q3 to Q4 is pretty accurate, but if I did it like that with some partition breaking this up, that this is underestimating, underestimating, underestimating. And it probably is a general an underestimation. Okay. But if we add up, if we make the partition better, right, more and more line segments, then we're going to get a little better approximation. So this approximation would be better. Okay, so that's the idea. And of course, even if you just half all those, it's going to be a lot better. Like that. All right, so that's much better approximation if you put in more and more line segments. Okay, so you should start really seeing a theme by now, basically. So we're going to define smooth. Okay, so definition. A function f is smooth on, and then we're just saying a closed interval because it could be smooth on a closed or everywhere. Could be the reals, whatever. But smooth on a closed interval if f prime is continuous on that closed interval. So not that f prime exists, right? That's different. Smooth means f prime is continuous. That's what we mean by a smooth curve. Okay. So now let's go through more of the derivation of a arc length. So let's f. Oh, little reminder back here, a little note. Let's see. Let's do this in blue. Look up the mean value theorem. I'm going to be using that. I'm not going to want to stop and go back and review the whole thing. That's partly my notes too for later whenever I use this again. So let f be smooth on a closed interval. So let f be smooth. Can't write. Okay, so let f be smooth on a closed interval from A to B. Let P be a partition of AB, and let Q sub K, so that's Q sub K is going to be one of these guys, right? One of these arbitrary ones. So let Q sub K be the point and the point will just be the x sub K and f of x sub K, like the function value on f, on the curve f. I'll just say f, it's fine. So it's going to start looking like this. Let's do a graph, general graph thing. So here's x, here's y. And so we're looking at maybe the length of that curve. And we'll say this is Q naught. And we'll say this is Q sub n. And so we're going to go to here. That'll be Q1. Q2, you get the idea. Oh, and then let's see. This would be q sub k minus 1, and this will be q sub k. And so, just like we were doing there a second ago, we're going to look at these lengths. That length, that length, this length, this length. Okay, I'm going to highlight that one in red. And this length. Okay, so then down here, is down on the graph, here's your x naught. This is your partition. This is x1, x2, and here's your x sub k minus 1, x sub k, and then we called this one x sub n, although it doesn't look quite like that. We're going to define, I'll just define it here. So delta x sub k is as before. That's x sub k minus x sub k minus 1. I need to fix something here. Hold on. Don't go anywhere. Oops. Okay. Where am I at? All right, so then let L be the length of the curve on A, okay, of the curve on AB. So basically I'm saying we know the length actual, so it's the actual length. So the length is the actual length here. Essentially what we're going to do is we're going to set up an approximation for L. And then when you take a limit, it gets to be exact, right? So just like we've done with other stuff, other areas and stuff. Okay, so then, and this is all set up. This is all set up for when we do the Riemann sum. Okay, so then next, let D q sub k minus 1 to q sub k be the length of the line segment between q and qk. So be the length of the line segment between q sub k minus 1 to q sub k. Okay, so we're developing this, bit pretty much as rigorous as I've done it in calc class so far, I think. This is the real deal here, finally. So L, we can say, is approximately the sum, k goes from 1 to n, of all those lengths of q sub k minus 1 to q sub k, right? I mean, I'm just saying that this is each of these lengths. And then L is approximately this sum, whatever that may be. Okay, so that makes sense. Okay, where was that? I almost went too far. Now let's take a look at what d q sub k to k is using this notation. So d of q sub k minus 1 to q sub k is equal to, so what is that length? when you put in the function values. So remember that, it's coming back over here, so just pick this one. So you have basically f of x sub k and xk. So that's that value. And then this value here would be the same thing with k minus 1. So I guess I can put it in there. So it's x sub k minus 1 to f of x sub k minus 1. So that's what we're looking at there. So it's equal to the square root of, and this is the distance form, that's why I did it above, x sub k minus x sub k minus 1. The order doesn't really matter, right? Because you're squaring it. And then plus the function values. F of x sub k minus f of x sub k minus 1. And then we square that. And then we put the radical all the way across. Okay, now we're going to apply the mean value theorem. So the mean value theorem says if f is continuous, that there exists, well, let me just write it out for you. So, and then we'll talk about it. So by the mean value theorem, so look it up right now if you have a chance, MVT, there exists a W sub k in this interval, x sub k minus 1 to x sub k, such that, that means such that, f of x sub k minus f of x sub k minus 1 is equal to, and then it's, you get the f prime. So there's a, basically it's the same slope situation. So you're going like this, and you have a secant line. There's another value that gives you that tangent line. That's the idea. So there exists a value here that gives you the same slope as the secant line. So this is a distance, basically, and then we're saying, well, there's a value c that gives you essentially that same result. The slope's the same. We're using that concept and then substituting in. Okay, so look that up, see why you get that c. I'm just using w sub k because we have the subscripts of k. So f of x sub k minus that equals f prime of w sub k times x sub k minus x sub k minus 1. And there's other forms of that. Sometimes you see f prime is equal to that difference. So it's equal to the difference of the y's. This is the secant line between the k's right there. So there's another value in between. I guess I could even show you here. There's another value in between. Maybe it's that dot I put down that gives you this same tangent line. Okay, so maybe, I don't know where it's going to be, but right there. And so that's the same slope, basically. So there's some value in there that gives you that tangent. There's your w sub k. That's what it's saying. And then we're going to use the result of it to basically finish our theorem derivation. So this is your delta x sub k. So we're going to basically substitute this stuff with this instead. So that's equal to f prime of w sub k delta x sub k. So now we can make that substitution. So therefore, d of q sub k minus 1 to q sub k is equal to the square root of, and you see what this will allow us to do, that's delta x sub k, and then we're replacing this with this. That allows us to factor out the delta x sub k. So this is delta x sub k squared plus f prime of w sub k, delta x sub k, and then that whole thing is squared. So we can factor that out and then take the square root of the delta x sub k. So this value here is going to be factored out because it's this in both terms and it's squared. And then that allows us to simplify it further. So it's the square root of, and if this doesn't make sense, we can go over it later. It's some algebra. Spend some time on the algebra here. So you get all of that, and it's squared. Might run out of room here, huh? And then times your delta x sub k. Okay. Oh, and notice that since delta x sub k is positive, you drop the absolute value. So basically, just to be clear here, so when you do the square root of a squared, that's absolute value of a. But if a is positive, then you just write a. So that's what I did down here. That's what happens there. Okay. Now take a limit as normal the partition approaches 0, and you get the definition of arc length. Isn't this awesome? So L is approximately the sum over all the k's of that square root of 1 plus f prime w sub k squared delta x sub k. The length of that curve is approximately the sum of all those. So that's what you do. So now take a limit as the norm of the partition approaches 0. And you get the definition. So the definition of arc length we say this. Setup's just smooth. So this is just a hypothesis, though. So let F be smooth. On AB. And then we use S for arc length. So S is equal to the integral from A to B. Because that when you take the limit of this, that's Riemann sum. Well, including that, when you take the limit of that as a norm of the partition approaches 0, that is the Riemann sum, which equals, or by definition, is the definite integral. So integral, and then you get the square root of 1 plus f of x squared dx. And that's it. Oops, f of x prime. Oh, well, Mike, there's got to be a prime in there. So it is not clear at all if I just gave you this formula where the f prime squared would come from, or even the 1. So that's what this derivation basically shows you. This doesn't just pop out of thin air and it works. All of this above is why it works. And it boils down to applying the mean value theorem to getting a form. So you're using the form of the mean value theorem. You're not really applying it as a like directly. It's just that we can reduce it to a nicer form. So you take the derivative of f, square it, add 1, square root. Now this can be kind of messy, but that allows us to apply the definition of Riemann's sum. Okay, so there's your derivation. Let's look at some examples, and then move on. Okay.